everybody. So we are going to continue our discussion in physics, and so far we've really been harping on this idea of motion. Why do we talk about motion so much? Well, motion underlies most physical phenomena, so we really want to spend some time to drill down into these ideas of motion. We've talked about quantities that describe motion. What are those quantities we use to describe motion? Position. Position is a great descriptor of where an object is located. If our position changes, we might use the physical quantity of what to describe a changing position? Displacement. Displacement describes our change in position. And I heard it over here, but displacement usually takes some time. If we want to know the rate at which displacement occurs, meaning the rate of change of position, what are we looking for? Velocity, absolutely. Velocity. Velocity is the rate of change in position, and I really want to get us comfortable with thinking about things in a sense that is related to calculus. So we'll say derivative of position with respect to time. This is a way to write the rate at which displacement happens. And then, of course, velocity often changes. Objects start at zero speed and speed up. Objects churn. These are all cases of velocity changing. And if velocity is changing, we say an object is what? Accelerating. Wonderful. So then we have acceleration. Acceleration being dv dt. And we've looked at several different ways to represent our motion so far. We've looked at motion that is vertical, up and down. In the case of vertical motion, we might use y to represent our position. We might use x to represent our position left and right. But last time we introduced another idea. We introduced another idea in which we talked about an object not necessarily moving strictly left and right or strictly up and down, but something moving in both x and y in a circular fashion, and in which case we might use theta to represent the position of an object. Theta, along with a radial distance to an origin r, but in circular motion that r value stays the same. So theta is a changing value. We have what we call translational motion. Translational motion being the Cartesian coordinate system that we're familiar with. We have this translational motion. We also have what we call rotational motion. Translational motion and rotational motion. And any motion we look at, we can describe using either quantities. Sometimes it's more convenient to use one or the other, but any motion can be described with either translational or rotational motion. So then the question becomes, if we can describe any motion either way, how do we connect the two, right? Because we've seen translational motion, and we've seen, you throw a rock into the air or something, and you ask the question, well, how is position related to time? And you see, okay, well, y equals y naught plus velocity in the y direction times time plus half acceleration in the y direction times time squared. We have strictly a translational way to look at a rock being thrown through the air. And this is a perfectly fine way to do it. This is one of our kinematic equations. But then we looked at rotational motion. We said, well, how does rotational motion behave? We say, okay, an object is rotating. If an object is rotating, we might have some theta value that we are concerned with related to some angular velocity, omega, and some angular acceleration, alpha. So we look at things pretty separate, right? We look at an object spinning through the air. We said that's rotation. We'll use theta, omega, and alpha. We look at a rock being thrown into the air. Well, we'll use y, v, and a for acceleration. And we've solved a couple of problems using this idea. But now the question becomes, how do we relate these values? How do we relate theta to a distance traveled if we want to know how far something has traveled during a rotation? And I'm sure we've all seen this relationship in mathematics before. I'm sure we've all taken geometry where we were asked a question, perhaps a question similar to looking at the moon, and look at the moon as it rotates around the Earth. I'm going to use E here for Earth, not to scale. So we have the moon rotating about the Earth. We ask the question, well, how far does the moon travel during its motion? How far does the moon travel during its motion? We can answer this question of how far a couple of different ways. How far does it travel? We can answer this question with our rotational quantities. How far does it travel? Well, it travels 360 degrees, right? It travels one revolution. So we might say delta theta is equal to one revolution. That is a way to describe its displacement. It undergoes one revolution during an orbit. We might say that it's 360 degrees. That is another way to represent its angular displacement. And that's perfectly fine. But what if I wanted to know what the actual distance, how many meters it traveled? I'm going to use delta S here. Why did I use S? Because it's not going to be a change in X. It's not going to be a change in Y. So I'm going to use S as this sort of arbitrary variable to say this is how many meters it travels when it goes throughout one orbit. That blue line I just drew there, that is your delta S. That is how far it travels. So I ask the question, how far does it travel? How do we mathematically figure out the distance it travels? Any ideas? Circumference. Circumference is the distance around the circle. So circumference will tell you how far that it traveled. And in this case, we have it going around the circle. How do we calculate the circumference? 2 pi r. 2 pi times the radius. Not so bad, right? So then we ask the question, how far is the moon away from the Earth? Let me get this right. 4,400,000 meters. 384,400,000 meters. That's how far away the Earth is from the moon, meaning that is our radial distance. So we want to know how far, in meters, does the moon travel during a single orbit? How far does the moon travel in a single orbit? Well, we'll take 2 pi and multiply it by this radius, 384,400,000. I'll give you some value. Go ahead and calculate it out real quick. Check with your neighbor. Make sure you and your neighbor got the same value. All right, so you should have ended up with Was it 2 billion? What's after the 2 billion? 418 million? Yeah? 15 million. 415 million. 1, 2, 3, 4. And then Sigfig says, let's round off the thousands and the hundreds place. Did I get the right number of zeros there? 2,415,000,000, 0,000 zeros. So you get this huge distance, astronomically large distance. And that tells us how far the moon travels. We haven't really answered the question yet, though. We haven't really answered the question, how is delta S and delta theta related? I mean, actually, we kind of have. I haven't told you yet, but we have. But we have this value, 2,415,000. We then ask the question, what angle is made after traveling 1 billion meters? What angle is made after traveling 1 billion meters? Well, we have our Earth, we have our moon. The moon is going to travel 1 billion meters. 1,200,000,000 would be about halfway, right? So we are traveling a little bit less than halfway. Here's our initial position. Here's our final position. We pretend that I drew out a nice subcircle here. And the question is, what is the angular displacement, delta theta, during this motion? What is the angular displacement, delta theta, during this motion? And we think back, and I think at some point you probably would have seen your math teacher talk about this idea of arc lengths, right? How many of us are familiar with that word, arc length? And arc length being the distance subtended by some angle, delta theta. Right here, we have an arc length of some distance, delta s, and that arc length is dependent on delta theta. And delta s is dependent on delta theta. It's also dependent on the radial distance r. So delta s is dependent on r. The bigger the radius, the bigger delta s is going to be. And delta theta, the bigger the angle, the bigger your arc length is going to be as well. So these things are related to each other. And we define a certain type of angle. We define a certain type of angle by this arc length. We say that delta theta in a certain unit of angle is going to be the ratio of delta s to radial distance r. The angle is going to be given in a certain unit. The angle is going to be given by the ratio of arc length to radius. And this is the definition behind angle in units of radians. So if you ever wonder what a radian is, right? You look at your calculator it could be in degree mode, it could be in radian mode. Radians is defined to be a unit of angle that is simply a ratio of arc length to radial distance r. So then we ask the question, well, what is this delta theta going to be when we travel 1 billion meters? Well, delta theta is going to be the arc length that the moon travels during this time. Well, it travels 1 billion meters. So you say it's 1 billion, it's million, thousand, hundreds. And then we divide it by the radial distance, 384,400,000 meters. We can calculate out what the angle is. Go ahead and do so real quick. There, the answer in a couple of places. Be about 2.6. Yes, for the numerical value? Is that right? 2.6. And then we take a look at the units. Well, we're taking 1 billion meters and dividing it by 384 million meters. Meters cancels out with meters. We're left with no unit, right? We're left with no unit here. So delta theta here has no unit, and that's the interesting thing here. When we define our angle through this use of radians, we end up with something that is a unitless value. Why is that? Well, that's because we define the radian using a ratio, and ratios never have units. So what do we do here? Well, we want a way to understand what this 2.6 means. It means something to do with angles, so we attach this unit of radian. We attach this unit of radian to it, but the radian is a sort of pseudo-unit. It's not a real unit, meaning that when you do mathematics with it, it's not really going to be there. It gives you an indication of what you're talking about, but we'll see cases where we kind of ignore it when we start to do algebra. All right, we come back here, and we look at this and we say, okay, well, we travel some delta S. We calculate that out to be about 2.5 billion meters. We have some radial distance of 384 million meters. And then we ask the question, okay, well, what is the ratio of delta S to radial distance? Well, algebraically, that's just going to be 2 pi, right? We see that from our equation. We used this equation earlier, worked. So it still applies. I haven't changed anything about the situation. So if we just want to know arc length divided by the radius for our full circle, it's just going to equal 2 pi. We come over here and we say, well, that's also how we define delta theta. It's also how we define delta theta. So we say that the angular displacement is going to be 2 pi radians. And this is why we define the circumference of a circle to be 2 pi times the radial distance. It's coming from this definition of radians, where we say that the angle in radians, 2 pi radians, is equal to delta S over R, the ratio of arc length to radius. So we might say delta theta for a full circle is, yes, 1 revolution. Perhaps we say it's 360 degrees. Or we can say it's 2 pi radians. A full rotation is 2 pi radians. Sound all right? Any thoughts and comments? It's not so bad so far, right? We're going to look at a new system. We're going to look at the Sun and Earth system. We're going to look at the Sun and Earth system. For the Sun and Earth system, we can take the distance to the Sun as being 149.6. I'm trying to get this right. 149.6 million kilometers. Note the unit, it's kilometers, not meters. So we have this distance to the Sun, we have the radial distance, wonderful. I might ask the question, if the Sun undergoes an angular, or sorry, if the Earth undergoes an angular displacement around the Sun, if it undergoes an angular displacement around the Sun of 190 degrees. Important note about units here, 190 degrees. Then my question might be, what is the distance that it actually traveled? What is its arc length? How far did it move from start to end? So we're looking for it to go 190 degrees. That'll take it to somewhere around here. So this is initial point, final point. about 10 degrees below the negative x-axis if we wanted to think about it. So the question is, how do we calculate this? Well, I gave you a great equation earlier. I said that the angular displacement delta theta is defined to be arc length over radius. So we think, okay, let's go ahead and try that. We say delta s is therefore equal to delta theta multiplied by r, multiplied by our radial distance. We have delta theta. Delta theta is 190 degrees. We have r is 149.6 million kilometers. But there's an issue here, and there's an issue here in our units. The degree. The degree is a non-SI unit. We need to do a unit conversion. In fact, a degree is a kind of arbitrarily made unit. One day someone just decided a circle is going to be 360 degrees. There's actually a very good reason why someone made that decision, but it was kind of arbitrarily made. 360 degrees has no basis in mathematics, whereas radians has a meaning. It's a ratio. So radians come from a very real place, whereas degrees are kind of made up. Whenever we're doing these rotation problems, it's probably a good idea to convert to radians. So we want to convert to radians, and to do that, we set up a unit conversion factor. We say delta theta is going to equal 190 degrees, and then we put a unit conversion here, and we say, well, what is our unit conversion going to be? We want to end up in radians. We want to go from degrees. All right, and then we ask the question, well, what is our relationship? We know 360 degrees is the same thing as 2 pi radians. So we can do 2 pi radians divided by 360 degrees. So you take 190, we multiply by 2 pi, we divide by 360. That will give us our angle in radians. The degrees cancels out. So we end up with something. It's going to end up being a little bit bigger than pi. But we end up with our unit in radians. Now that we have our unit in radians, we are free to use this relationship, that delta s is equal to delta theta times r. So we make a mental note. Must be in radians. Not degrees, not revolutions, must be in radians. Okay, so go ahead, work it out in your calculator, share it with your neighbor, figure out what the arc length is going to be for the Earth as it travels around the sun to subtend an angle of 190 degrees. It'd be a good idea to check with your neighbor, make sure you have the same angle of radius. While you're doing this, I do recommend that you pull out those little note cards that I handed out. All these equations are on it, and it's nice to see where they come into play. So, not here. So, there's a good question, great question. Do you need it in degrees of radians for your calculator? Right here it doesn't matter. Right here it doesn't matter because what degree mode and radian mode does is it deals with when you take sine of an angle or cosine of an angle. So when you use those trig functions, when you use a function with an angle, then it matters. You need to make sure that that angle is in degree or radian. But here we're just doing multiplication and division. Since we're just doing multiplication and division, it doesn't matter which mode you're in. So here it doesn't matter when you're doing trig functions as well. Raise your hand if you want a little bit more time to find the arc length of the path. All right, seems like we're mostly there. Does someone want to venture out a guess as to what the arc length is? Raise your hand if you want to let me know what your answer was. I will randomly call on someone if no one raises their hand.
494 million. It'd probably be 494.
494 million watts. Wow. We could write 494 billion meters if we wanted to. 1,000 meters to a kilometer. Do we feel all right about this? All right. It's not so bad. Not so bad, right? So then we ask the more general question, how do we go between a position in translational motion, delta S, and an angular position, or more specifically, I should be putting this in displacement. A translational displacement delta S is equal to R times delta theta. This is the relationship between our angular displacement and our translational displacement. Do we feel good about this? Any thoughts, any comments? All right. We feel good about this. Then I'm going to ask the next question. So we have this way to translate between translational motion and rotational motion as far as our displacements go, and that's wonderful. The next question might be, well, how fast does the Earth move? And I use that word specifically, fast. How fast does the Earth move during one full orbit? I put an S there instead of a T. If I learn how to spell, that would be great. During one full orbit around the sun. And I use this word fast because I specifically want to look at speed. I want to know how fast the Earth is going. That's speed, not velocity. And why do I make this choice? Well, I make this choice because the Earth, as it moves throughout its orbit, when the Earth is located perhaps at this point around the sun, it is going to be moving, generally speaking, up and to the left, right? When it's on the opposite side of the sun, when the Earth is over here, it is going to be moving more down and to the right in that part, right? And anywhere you look, well, the Earth's velocity is going to be pointed in a different direction. What does that mean? That means that the direction of the velocity vector is always changing. When an object is undergoing circular motion, the direction of the velocity is always changing. However, there is a subdivision of circular motion that we often care about, and that is the case of uniform circular motion. For uniform circular motion, we accept the fact that the velocity is always changing by virtue of the direction changing. But with uniform circular motion, the magnitude of that velocity is a constant. The magnitude of the velocity is a constant. That's a fancy way to say the speed is a constant. So yes, it is changing directions, but it's not speeding up, it's not slowing down, it is just turning. We have a changing direction, we have a turning object, and it's always turning inwards towards the sun, but we have something that is always turning, not necessarily speeding up or slowing down. The Earth is a great example of that. It maintains relatively constant speed. So the magnitude of velocity, or in other words, the speed, is a constant value. If speed is a constant, we can figure out what that value is. We've done this a few times. We might say the speed, and I'm going to use v without an arrow on top to represent speed. The arrow on top means I care about direction. The arrow on top means a vector. Without that vector arrow, we're saying that this is just speed. And to find speed, well, that's not too hard. To find speed, we just take displacement over time. Displacement over time. Well, what is the displacement? We can figure out what the displacement is of the Earth orbiting the sun. How do we find that? Well, we just take the radial distance multiplied by delta theta. For one full orbit, what is our change in angle? Well, 360 degrees, that's okay. That's an okay way to represent it, but more often we'd rather use a different unit. How might we represent one full rotation using a different unit? 2 pi radians, right? So we might say, okay, in this case, delta theta is 2 pi radians. 360 degrees is absolutely true. It is 360 degrees. We can also say it's 1 revolution. But for the case of rotational motion, we often like to use radians. Radian is a unit that actually means something. Degree is arbitrary. I gave you the radial distance, some million kilometers. So we have a way to figure out delta S, and then the question is t. T. When an object undergoes one full circular rotation, we call this the period of rotation. The period of rotation is the time to undergo one full motion. The period of our orbit is the time for us to go around the sun one full time. Now, pop quiz, how long does it take for the Earth to move around the sun? 365 days, well, kind of. Every 4th year, how long does it take? 366 days. We get an extra day in those leap years. Why is it that we get that extra day? That's because the period for the Earth to go around the sun is actually about 365 and a quarter day. Fun fact, it's actually closer to 365.26 days. To account for that extra 100th of a day, every 100 years we skip a leap year. The year 2000 was not a leap year. But this gives you the time period in days. Of course, we generally want SI units of meters per second. So we'd have to do some unit conversion. How many hours are in a day? 24. So we take that number, multiply it by 24. That gets us to hours. How many minutes are in an hour? 60. So then we take that, multiply by 60 to get it into hours. How many seconds are... All right, we do that, we get it in minutes. How many seconds are in a minute? 60. So we take 365.26, multiply by 24 by 60, and that'll get us to seconds. So here's what I want you to do. Calculate out for me what the speed is of the Earth as it moves around the sun. What is the speed the Earth moves around the sun with? Meters per second. You could do kilometers per second if you want to just stick with kilometers. Earth moves quite quickly. All right, it needs a little more time. All right, majority rules, we are going to move forward. We're not going to say out loud what this answer is yet. We're not going to say what the answer is out loud because we're going to derive a new way to find just this same answer. We're going to do it by taking a look at the algebra that we're doing. We say that the velocity is given by delta s over time, and that is absolutely true. And then we say, well, I know how to get our arc length or displacement delta s from delta theta. We say that that would be radial distance times delta theta over time, right? Without plugging in numbers, we say that this is the algebra that we're doing. We multiply our angular displacement delta theta by the radial distance r. Rearranging this a little bit, we have r times d theta over time. Change in position over time, change in angular position over time, we define that to be our angular velocity. V is equal to r times omega. Our angular velocity, omega. Then we take a look at this, and we now have a way to go between translational velocity v and our angular velocity, omega. We'll check if it works. We'll check if it works by analyzing once again the Earth and Sun system. The Earth rotates around the Sun. The Earth rotates around the Sun at an angular velocity of what? 1 revolution per year. We revolve around the Sun 1 time in a year by definition. By definition, this is true. But this is not our SI unit. Instead, we might convert this to our SI unit of radians per second. How do we do that? Well, we have 1 revolution per year. We then take this and we say, I can convert to our SI unit of 2 pi radians per 1 revolution. And that'll put us in radians per year. 2 2 pi radians per year. Well, that makes sense. We undergo full rotation, full 2 pi radians in 1 year. That's good. We want to convert it to seconds. So what do? Well, we multiply it now by 1 year is 365.26 days. Ran out of room there. And then you multiply it to go from days to hours, 24 hours in 1 day. Nope, got that backwards. 1 day divided by 24 hours. And then you take this and you get it into seconds. I'm going to skip a second and say 3,600 seconds is 1 hour. And that'll give you your angular velocity in radians per second. Once you have that in R, you can multiply them together to find the velocity. I'm going to have you do just that. Figure out the velocity now through this new method of first finding out what the angular velocity omega is, and then multiplying that by the radial distance. All right, who needs more time to do this? Raise your hand. Okay, now I want to ask the question. Is the velocity you found the first way and the velocity you found the second way, you get the same results? Yes or no? Should have. It might be different by rounding. If you didn't round at all, you would get the same exact answer. But either way, you should have gotten the same velocity. What does that mean? That means that we have a way to go between the translational delta V and the rotational, or sorry, not delta V. We have a way to go between the translational velocity V and the angular velocity omega. Now we take a look at those two equations. Delta S is equal to R delta theta, V is equal to R omega. Take a look at those. We absorb them in our minds, and we might notice a pattern. We might notice a pattern. I want you to turn to your neighbor and tell you what you think that pattern is. What is the pattern? While you do that, I'm going to erase part of the board. Who wants to? All right. All right, I'm going to pick on someone. In the back. What do you notice about these two equations? What is the relationships? What do we notice about these two relationships? Not sure? Okay. Let's pass it on. Let's go with in the red shirts. What do we notice about these two relationships?
We were saying that whatever the unit we're looking for is multiplied by the radius, so I think acceleration will be multiplied by the radius.
Okay, hold on. We have a prediction here. Acceleration is going to be what?
Multiplied by the radius, like it's what
Something like that? Great. We use this pattern. We see a pattern, and you're absolutely right with the pattern. We take our radial distance and we multiply it by our angular quantity to get our linear quantity, our translational quantity. So we have acceleration as our alpha is our guess as to what our acceleration relationship is going to be. Now, what does this type of acceleration look like? Let's just start off with the question, what does this acceleration look like? Last time we did a question where we looked at a record. We looked at a record and we said our record went from some initial velocity 0, initial angular velocity 0, and it sped up to 45 rotations per minute. We looked at this last time. We said, okay, record spins up to 45 rotations per minute. We undergo some change in angular velocity. We have a change in angular velocity. That's what this acceleration alpha is looking at that spinning up, or spinning, slowing down, either way. So that's what alpha is. What is A? A is taking a look, perhaps we take a look at some point on the spinning object. We take a look on the spinning object, we say, let's look at that point right there. Just arbitrary location. We take a record, we mark on it with some X. We say we look at that point. Initially, this point has 0 velocity. It's not moving because the record isn't moving. But as the record spins up, that point becomes, it starts to move faster and faster. This point might be a distance r from the center location. So we ask the question, what is the acceleration of that point? Now we do the derivation. Our derivation is going to be a little bit more intensive this time. Why? Because I trust your mathematical skills. We're going to delve into the world of calculus for this next derivation. We could do it the same way we just did, but we're going to do things a little bit differently because I want to push you guys to think about the calculus nature of everything that we're doing. In calculus, we say acceleration is the rate of change of velocity, dv dt. Acceleration is the rate of change of velocity. We take a look at this and we say, well, velocity, I found out a way earlier to find velocity given omega. What does that mean? Our acceleration can be rewritten as the derivative of r times omega. Not too bad. Not too bad. R is a constant as an object rotates in circular motion. it traces out a circle, and on a circle, the radial distance does not change. R is a constant, and anytime you have the derivative with a constant in it, you can pull that constant out. A is equal to R times d omega dt. D omega dt. Last time we did something with that. Last time we saw it. Last time we saw that, and that was in a definition that we used that to define our angular acceleration. Acceleration is equal to r times angular acceleration alpha. And what do you know? We end up with the relationship that was predicted. That we take our angular acceleration, we multiply it by the radial distance, and we get our linear acceleration. So this is a way for us to find our acceleration of our rotating object. Well, kind of. This is half of the answer as to what the acceleration is. There's another half. Because when we look at this acceleration, this describes the speeding up and slowing down of this point on the record, for example. This describes our speeding up and our slowing down. But acceleration means changing velocity. Velocity is a vector. Vectors have two pieces to them. What are the two pieces every vector has? Magnitude and direction, absolutely. This describes the changing magnitude of our velocity. The changing magnitude. It does not describe the changing direction. We have to use another type of acceleration for this. This describes the changing magnitude. And we'll look at that in just a moment, the changing direction part in just a moment. Just know this is half of the answer. This is one type of circular acceleration. So when we take a look at this, A is equal to R alpha. We can start to apply it to a problem, perhaps. Let's start to apply it to a problem. Let's look at this record example. This record example where we have some change in angular velocity, and I'm going to give it some random time. T is equal to 1.3 seconds. I don't remember what I used last time, but we'll use this time. Let's say it takes 1.3 seconds to get up to speed. I want to look at some point on the record that is a distance of, we'll say, 5 centimeters from the central axis. That's the point we're looking at. Different points will have different accelerations. So we'll just look at this 5 centimeters. We want to calculate out what is the linear acceleration A. What is the linear acceleration A going to be? Well, how are we going to do this? We're going to figure out what our angular acceleration alpha is. How do we do that? We go back to our kinematic motion equations. Our kinematic motion equations, which might say that your final velocity is your initial velocity plus acceleration times time. We have time, we have final velocity, we have initial velocity, final acceleration. So first step might be to find angular acceleration through those kinematic equations. Second step would be to multiply that angular acceleration by the radial distance r. Keep in mind that we don't want rotations as our unit of angle. We want radians. We don't want minutes as our unit of time. We want seconds. So we have to convert to our SI units of radians, seconds, as well as r in meters. That is our goal. So we're going to go ahead, we're going to find the acceleration. I'm going to give you a couple of minutes to do so. Find the acceleration. Again, do your unit conversions, then alpha, and then A. That is the path. so however far you got, let's go over this real quick. First step, unit conversions. Omega naught is still 0. 0 radians per second squared, doesn't matter what unit system we're in. It's not moving, so its initial angular velocity is 0. After 1.3 seconds, our velocity increases to 45 rotations per minute. How do we get it out of rotation per minute to radians per second? Well, we're going to multiply it by 2 pi and then divide by 60. And when you do that, you should end up with 4.7 radians per second for our final velocity. Just as a double check, if you guys ever want to check on it and you want to take note of this, going from rotation per minute to radians per second is almost dividing by 10. It's not quite dividing by 10. It's almost. So we go from 45 to 4.7. All right, well, once we have this, we find our angular acceleration by taking our change in velocity and dividing it by time. When you do this, you should end up with, if I did my math right, 3.6 radians per second squared. How many of us got this one? Wonderful. What do we do from here? Well, from here we would find our acceleration by taking our angular acceleration, multiplying it by our radial distance. Angular acceleration, 3.6 radians per second squared. Multiply that by our radial distance r, that is 5 centimeters or 0.05 meters. And you get an acceleration of 0.18 meter per second squared, an extra unit of radian on the end. And we look at this and we say, well, that is almost our unit of acceleration. Our unit of acceleration has typically been meter per second squared. Here we have that extra value of radian. Why is that? We go back to our definition of radian. Radian was defined to be a ratio of arc length to radial distance, meter over meter. Radian was a pseudo unit, and this is what I mean when I say it's a pseudo unit. We attach it to things when we're talking about our angular quantities, radian per second squared, radian per second. But it is just there to give us an indication that we're talking about rotational quantities. When we're talking about translational quantities, we get rid of that pseudo unit, giving us our meters per second squared. That is our acceleration. Well, again, this is only half of your acceleration. There's another half of acceleration. What is that other half of acceleration? Well, this is acceleration that tells us about our changing magnitude of velocity, but it doesn't tell us about our changing direction. For our changing direction, we talk about a centripetal acceleration. Centripetal acceleration is the type of acceleration that deals with changing direction of a rotating body. And when we look, for example, at our Earth and Moon system, our Moon undergoes a circular rotation around the Earth. It's roughly circular enough. And when it does this, we can track the Moon at different points. We can say at this point the Moon is moving with some velocity that is vertically up and down, right? A little bit later, velocity will be tilted. When it's up at the top, the velocity will be directly left. When we're down here, the velocity is down and to the left. And in fact, at every point, the velocity is going to be tangent to the circle. We look at this and we say, well, at this point, our velocity goes from vertical to some angle. It's undergoing a shift, pointing inwards towards the circle. We look up at this point. It's going from vertical to sort of up and to the left to horizontal. It's going through a shift that is pulling it in towards the center. Our velocity, again, is going through a shift that changes its direction to point it in towards the center. It's this acceleration as changing the direction is always getting the velocity to pull inwards towards the center. And we'll see the mechanism behind why this occurs. But this acceleration always pointing inwards is where this type of acceleration gets its name. Centripetal is Latin for center seeking. This centripetal force centripetal acceleration, jumping the gun here. The centripetal acceleration always has a direction that is inwards towards the center. And you ask, well, how do you find the centripetal acceleration? There's a longer derivation to be shown here that I am skipping over. Why am I skipping over it? I don't think there's a ton of value in deriving this, and we'll see later a better way to look at this. But the centripetal acceleration can be found by taking v squared and dividing it by the radial distance. V squared, v is your translational velocity, not your rotational velocity. Your translational velocity squared divided by the radial distance. This is your centripetal acceleration. Your centripetal acceleration so you have this centripetal acceleration always pointing inwards. If our object were speeding up, we ask the question, which way is the acceleration going to be? Well, if something is speeding up, we've seen this in lab. If something is speeding up, that means its acceleration and its velocity are in the same direction, right? We've seen that in lab over and over. If something is speeding up, the acceleration and the velocity are both positive, or both negative. If it's speeding up, they share direction. Meaning that this earlier acceleration that we found, alpha times r, when we look at our rotating object, we had a record with some point on here. Its velocity was tangent, so was its acceleration. So this point on the record, it has an acceleration pointing tangent to its motion, causing it to speed up. There's also a centripetal acceleration causing it to change direction. The acceleration, r times alpha, is often called the tangential acceleration, and is always perpendicular, always 90 degrees to the centripetal acceleration. So it's an important point to note. The acceleration that we found here is tangent to the motion. Centripetal acceleration is always pointed radially inwards. And they're always 90 degrees to each other. So then we ask the question, well, how do we calculate this angular acceleration? What is a problem we might find? Well, a problem might be defined as what is the centripetal acceleration of the moon around the Earth. There is no tangential acceleration for the moon. It travels at roughly a constant speed. But it does have a centripetal acceleration, causing it to change its direction. Again, the centripetal acceleration changes direction. How do you find this? Well, you might start with v is equal to omega times r. I gave you the value of r earlier. Omega is how fast it goes around in a circle, right? To find omega, you'll need the period for the moon around the Earth. Pop quiz, who knows how long it takes for the moon to go around the Earth? Any guesses? Who here ever pays attention to the calendar when it says full moon, new moon? How long is between two full moons? About 30 days. Yeah, about 30 days. For those of you who don't know, the period for the moon to go around the Earth, about 29.5 days. A little less than a month. That's how we created months. So a month is roughly the time it takes for the moon to go around the Earth. It's been changed a little bit over the years, but 29.5 days. So you can find omega, you can find r, you can find v. Once you have v, you just do v squared over r. That gives you the centripetal acceleration. But is there a better way? We have v squared over r. That absolutely gives you the answer. And this is all in terms of translational quantities. What happens if we want to use our rotational quantities, right? We have centripetal acceleration is v squared over r. We also have that velocity is omega times r. So what can we do here? We can say our centripetal acceleration, v squared over r. We can rewrite that by algebraically replacing our velocity with omega times r. Yes? And we look at this and we say, well, we can distribute that squared. It's going to be omega squared r squared over r. One of those quantities of r cancel out. That means your centripetal acceleration can be found by omega squared times r. So we have a centripetal acceleration that can be found with omega squared times r or v squared over r, whichever path you'd want to take. And this gives us a complete description of how we find the relationship between our translational displacement, velocity, and acceleration, and our rotational velocity, and our rotational acceleration, and our rotational displacements. Takeaways from this lecture are this, that you can translate between the different methods of analyzing motion. You can go between translational motion, meaning your Cartesian coordinates, x, y, and z, and your rotational thetas and r's. You can translate between them using these 4 mathematical models. When we approach problems using these values, it is incredibly important to remember to always use what for our unit of angle? Radians. You always use radians here. Never degrees, never revolutions, always radians. These equations were derived specifically from that definition of radian, meaning that these are only true under the case that we are using radians. So we must always use radians in these equations. Your displacements are in radians. Your velocities are radians per second. Your angular accelerations are radian per second squared. You must always use radians for these. That doesn't mean you have to put your calculator in radian mode. That's only when you're using trig functions. In these cases, your calculators are fine in whatever mode because you're just doing multiplication division. That doesn't change based on your units. But you do need to make sure that you do that unit conversion to radians first thing. All right, are there any questions, any thoughts, any comments? All right, before you head out today, you have some homework that is due to me. Be sure to turn it in. If you did not print your homework, this is crucial. If you did not print your homework, send me your homework in an attachment before tomorrow, before midnight tonight, meaning tomorrow starts. Send me an email with it in an attachment before tomorrow. Print it out Monday, hand it in to me Monday. Sound good? All right. Also, if you guys want your homework ones back, I have your homework ones up here. You can come through and rifle through these assignments to find yours. And that's all. Have a good rest of your day.